As a Monday, we covered the concept of nonlinear programming problems with the two examples. We're gonna have this network problem, which is nonlinear programming problem, and we're gonna take a look at the evolutionary algorithm today. As you see the PowerPoint slide, and on this whiteboard, we have this kind of a network problem, which is a very similar diagram we have learned in chapter 5, network analysis. But today we're going to have a little bit different approach. That was linear programming and linear integer programming. But today we're going to have a nonlinear programming using different algorithm. So now, as you see this from this network diagram, maybe I can go. Let's see. Can read the problem from the textbook. Okay, so yeah, there is on textbook 388 nonlinear network flow problem. Okay, Safety Trends is a trucking company that specializes in transporting extremely valuable and extremely hazardous materials. Due to the nature of its business, the company places great importance on maintaining a clean driving safety record. This not only helps keep their reputation up, but also helps keep their insurance premiums down. The company is also conscious of the fact that when carrying hazardous materials, the environmental consequences of even a minor accident could be disastrous. Whereas most trucking companies are interested in identifying routes that provide for the quickest or least costly transportation, Safety Trends likes to ensure that it selects routes that are the least likely to result in an accident. The company is currently trying to identify the safest routes for carrying a load of hazardous materials from Los Angeles, California to Amarillo, Texas. The network in this diagram on whiteboard summarizes the routes under consideration. There are many different routes, but we only consider these routes as you see in this diagram. The numbers on each arc represent the probability of having an accident on each potential leg of the journey. Safety Trends maintains a national database of such probabilities developed from data they receive from the National Highway Safety Administration and the various departments of transportation in each state. So maybe the company has analytics team, they collect these kind of data from national database to figure out what are the accident rate through these feasible routes. So we're going to start from node 1. California, right? Los Angeles, California to Amarillo in Texas. So node 1 is starting node, and 10 is ending node. So node 1 is origin, node 10 is destination. So we want to go starting from node 1 to 10 through many different feasible routes. Anyway, between two nodes, there are accidents in the past, so they collect those information and calculate the probability of accident. So for example, from node 1, Los Angeles, California to node 2, which is Las Vegas, having accident, probability of having accident is 0.003. That means these numbers, probability having accident. So probability of not having accident should be 1 minus 0.010. So if we say probability of having accident is P, then the probability of not having accident is 1 minus P. So actually these numbers from node 3 to node 5. So let's say node 3 to node 5. The probability of not having accident from node 3 to node 5 is 1 minus probability of not having accident 1 minus 3.5. So we try to find route to minimize probability of having accident or maximizing probability of not having accident. So the company wanna find the safest route. So we wanna maximize probability of not having accident. So as we learn from network analysis problem, so let's say the starting point will have a value of -1, ending node will have +1. The other node would have 0 demand and so because based on balance of flow, it's going to have 0. Okay, now let's get started to find decision variables. So decision variables, if we select route from node 1 to 10 through 3, 5, 7, 9, then segments of 1, 3, 3, 5, 5, 7, 7, 9, 9, 10 will have values of 1. All the other road segments will have value of 0. So now let's think about origin node. Origin node, we just have outflow from node 1 to 2, 1 to 4, 1 to 3. So let's say that is y from 1 to 2, right? And then from 1 to 4, 1 to 3 should be -1. Like you see, instead of using x, we just use y because this is a binary variables. You can use a different label, but we just use as the textbook says. So if you choose segment 1 and 2, this will be 1. If it is not selected, there will be 0. Again, if you select segment 1 to 3, 1 to 3 will be 1, and the other segments 1 to 4, 1 to 2 will be 0. So this is -1 equal to -1. So we are not going to violate any constraint. So we're gonna do these for all other nodes. That is origin node. So what about the destination node? We'll have inbound flows from 8 to 10, 9 to 10 should be equal to 1. So if you choose either route, you only have 1 out of these 2 feasible inbound flow. So you're gonna have 1 for 8 to 10, while you're gonna have 0 from 9 to 10. If you select segment 9 to 10, that's gonna be 1, then 8 to 10 will be 0. Now what about node 2? So we're gonna have just a couple of nodes constraints to understand. So node 2's inbound flow will be 1 to 2. Yeah, only 1 to 2. 1 to 2. Then you have outflow 2 to 6 and 2 to 4, y 2 to 6 and y 2 to 4. So if you rewrite this, it's going to be y1 2 minus y2 6 minus y2 4 equals 0. So we're going to have a balance of flow using inflow and outflow. So what about node 4? That's a little bit longer than others. Inflow, you have three inbound flows, 1 to 4 plus 2 to 4, and inbound flow from 3 to 4. Right, equal to outflow is 4 to 6 plus y 4 to 8 plus y 4 to 5. Okay, this is the way how to see the balance of flows. Now, let's see what is our object function. So we okay, so before writing object function, I was asking what are the distant variables. We already mentioned if select 1 to 2, it's going to be 1 or 0. So our decision variables y12, y14, y13, and very long. So let's just make it simple. Xij is 1 or 0. If selected as part of route, otherwise it's going to be 0. So next step is define object function. The company safety trends want to find the safest route. So we're going to maximize probability of not having accident. Okay, so if you select segment 1 to 2, the probability of having accident will be 1, 2, right? So this is the probability of having accident if you drive through segment between node 1 and node 2. So that means the probability of not having accident if you drive through segment 1, 2 will be 1 minus 1 y12 times probability of having accident 1 to 2. So we're gonna keep writing this. 1 to 2, 1 to 3 is 1 minus 1 to 3 p13 plus 1 minus 1 4 times p14 plus something wrong here, right? You'll find there's something wrong. So we're going to calculate overall probability of not having accident, overall probability. So it's not going to be plus, instead we need to have times. And right. So now you see the pattern from here. Yes. See, there is no probability of having accident from node 1 to 1. There is no probability of having accident from node 2, from node 2 to node 2, because it is not circulating at the same node. So now if you want to make it simple, this, right? So 1 minus yij times pij right? Multiply by 1, 2. Instead of n, I equal 1, 2, let's say large I. Now, j cannot be equal to I. So this is a simplified formula of objective function. Then this is objective function is subject to these constraints. So do you have any questions so far? Then I'm going to open Excel file to demonstrate. Okay, now you're already familiar with this form. See, from to node, from Los Angeles to Las Vegas. If you select, it's gonna be 1. If you don't drive through this segment, it's gonna be 0. So this range of select route will be decision variables, and we have a probability of accident if you drive from node 1 to node 2. So probability of not having accident will be 1 minus this decision variable times the probability of accident. So like you see, 1 minus H6 times F6. So overall probability of not having accident will be like this. Here in this cell, we have a product function, right, with range of G6 and G23. It is not some product. Don't be confused with that. This is a product from this formula. Then on the right-hand side, there is a table to explain balance of flows. Then see Los Angeles is origin node with value of -1, while Amarillo in Texas is destination with a value of 1. All other nodes will have a 0. If it doesn't have a 0, that means traveler stopped there. That means a truck stopped at the city and is not moving forward. So it shouldn't happen there. So now see the balance of flow is using sum if function, but I explained in the chapter 5, so you may able to understand what it is. So once you formulate these on your spreadsheet and open data and click solver menu, then you will have solver parameters. Okay, so we are maximizing probability of not having accident on cell G24 by changing decision variables from A6 through A23. Then add constraints. So these inflow outflow, which is the balance of flow, should be equal to right-hand side, supply and demand. And these decision variables should be integer, no binary, but I think we don't have to set up at this time, but let's just have it just in case. Then click okay. Then check make unconstrained variable non-negative. Then you need to carefully select a solving method from the drop-down list box. Instead of using simplex LP in chapter 5, now we're going to use generalized reduced gradient algorithm for nonlinear programming. So you need to select GRG nonlinear from this drop-down list box. Then click solve to get the solution. Now you got the solution. So see segment from, okay, we're starting from Los Angeles and next step is Phoenix. So from Phoenix, we go to Flagstaff. From Flagstaff, we go to Albuquerque, New Mexico. From Albuquerque, we go to Amarillo in Texas. That is the best route which has the highest probability of not having accident for the company safety trends.